Welcome everyone to today's webinar, Dekati Webinar. My name is Markus Nikka and I'm a technical sales specialist. I'm working in the sales and services team. Formerly, I worked in the R&D, so this new product, I'm quite familiar with this product since the R&D time also. So today we will talk about our new product for secondary aerosol measurement, so Dekati Oxidation Flow Reactor. The presentation or the webinar is recorded and will be available later on our YouTube channel. If you have questions during the presentation, please write them to the chat box where everybody can see them, or to the Q&A box where I suppose I'm the only one who can see those and I can answer your question privately if that's what you prefer. So today's content will be as follows. So we start by introducing the concepts of primary and secondary aerosols, and then why the secondary aerosol and secondary aerosol mass is interesting, and why there's a lot of research going on this topic. Then we look at the methods, how the secondary aerosols can be studied. Then we focus on the oxidation flow reactors and the Dekati oxidation flow reactor in more detail. Then some measurement results from our product, from our instrument, done in the lab environment. Then some key benefits of the instrument, and some application examples where OFRs are used. Some of them are measured with our product, some with the other instruments. Then in the end, I will introduce the upcoming sample conditioning unit that can be integrated and used together with the product. So the primary aerosol, in this case, we've taken example, the engine exhaust aerosol. The primary aerosol already exists in the vehicle tailpipe. So we have the non-volatile solid primary particles, the soot particles, and then some smaller core particles originating from the engine. And then we have different gaseous components, for example, hydrocarbons. When this hot exhaust aerosol exits the tailpipe to the atmosphere, it cools down rapidly and starts to dilute. Mainly the rapid cooling leads to a situation where nucleation of new particles or condensation of semi-volatile gaseous compounds can happen. And this, of course, increases the aerosol mass. So this so-called fresh aerosol that is present 10 seconds, few minutes after the emission, contains the non-volatile primary particles and these small semi-volatile addition, condensate or nucleation. But when this aerosol spends long time in the atmosphere, it will go through chemical changes due to the presence of the different reactive species in the atmosphere. The most important reactive oxidative species are the hydroxyl radicals, which will then react with the compounds mainly daytime. These reactions, these processes are typically called as aging of the aerosol. So when these reactions occur, the volatile compounds present in the atmosphere that has originated from the emission source react with the oxidative species. These volatile compounds may turn into new compounds with low volatility and hence have tendency to produce new particles through nucleation or condensate on the existing primary and fresh aerosol. And this, of course, further increases the particulate mass that has originated from the emission source. So secondary aerosol mass refers to this aerosol mass produced in the atmosphere long after the emission through these chemical reactions. And this age exhaust or age aerosol combines the whole range of particles formed in the engine and the atmosphere. The hydroxyl radicals are formed in the atmosphere in the reaction between ozone and water molecules when there is high energy photons present. That's why the hydroxyl radicals are the most important reactive species during daytime. During nighttime, there's no hydroxyl radical production. So the term secondary aerosol is used to describe this additional particulate mass that is formed long after the actual emission to the atmosphere, and it's typically divided into two subgroups, inorganic and organic part. The secondary inorganic aerosol is formed, of course, from the inorganic gaseous precursors such as sulfuric dioxide, nitric oxide, so on. And the amount of the secondary inorganic aerosols can be modeled pretty accurately if we know the amount of these precursor gases originated from the emission source. Then, yeah, the number of these different precursors is small and the reactions are well known, so the modeling is quite accurate. However, the secondary organic aerosol is a bit different. The number of different precursors is huge, from 10,000 up to 100,000, and their chemistry is much more complex than the inorganic precursors. So the modeling is difficult and inaccurate, which leads to a situation where you have to measure, to do actual measurements to define the amount of secondary organic aerosol mass produced from certain emission source. Here I introduce concept of potential aerosol mass, so PAM. The potential aerosol mass describes the maximum amount of particulate mass that can be produced from a certain emission source. So it includes the primary aerosol and the maximum of secondary aerosol. The secondary aerosol, both the inorganic and organic, has the mass concentration has tendency to increase when the aging, as function of the aging time. We talk about OHO, hydroxyl radical exposure, or the photochemical age of the aerosol. So longer the aerosol and the gas is spent in the atmosphere, more secondary aerosol mass it will produce, in principle. But at some point, if the aging goes too far away, it actually, the reaction starts to decompose the produced aerosol mass, and the concentration, mass concentration, will actually go downwards. This is called fragmentation. But if we talk about potential aerosol mass, we try to find the maximum of the secondary aerosol mass. So why secondary aerosol mass is interesting? Volatile organic compounds and different inorganic gases are emitted from several different natural and anthropogenic sources, such as different industries, especially petroleum industry and other chemical industries, energy production, so boilers, power plants, biomass burning, etc. Transportation, agriculture, and as an example from the nature, boreal forests produce quite a lot of organic precursor for secondary aerosols. And this secondary aerosol mass has actually a significant contribution to the ambient particulate mass. So there's estimations that up to 50% of smaller than 1 micrometer particles mass is organic, and actually almost all of this organic particulate mass is produced to aging, so it's secondary aerosol mass. So it has a significant effect on the air quality and human health, and there's a great uncertainty on the effect of these aerosols on the radiative balance. So we don't really know what is the actual effect of these aerosols to the climate and climate models. One important factor is also that there's a lot of regulation going on that is focusing on the primary emissions, and the primary emissions have decreased quite dramatically, which makes the secondary aerosol fraction even more important than it was in the history. So nowadays it's not anymore enough to measure only the primary aerosol, primary emission. This is a growing field, still growing field in the aerosol research. A lot of abstracts in the conference. I made a small search today with Google Scholar. I searched for secondary aerosol, and there's a typo, but secondary organic aerosol, these were the keywords that I searched from 2010 to last year, and we can see both has significant increase in the number of results, indicating that more and more publication on the topic. There's not much commercial instruments to do this kind of measurements. It's quite top-level research and expensive analyzers, and not, yeah, and there are many research groups have decided to build their own systems to do this kind of measurements. There has also a conversation started about the legislative limits for the secondary aerosol. So that's something that probably will come more and more important in the future, as the primary aerosols are already regulated, but secondary aerosols are not. So how do we measure or study the secondary aerosols? One way to do these measurements are so-called smoke chambers, which are huge, from 1 cubic meter up to few hundreds of cubic meters large, typically Teflon bags, like presented in the graph on the right, picture on the right. This chamber is filled with the known mixture of aerosol sample. You have controlled conditions in the chamber. You have known humidity, so water concentration, the UV light exposure, and concentration of ozone. And these conditions are typically close to the atmospheric conditions. So the benefits of these type of reactors are that the conditions and timescales are same as the atmospheric, so we can say that the chemistry should be quite similar to the atmosphere. And when you do this kind of measurement, you can measure the secondary organic or secondary aerosol formation as function of aging time as the process slowly goes forward. The downsides of these are that you can't, it's almost impossible to move them. Okay, these smaller ones might be portable, but usually they are not, and they take a lot of space. And conducting a measurement is quite slow. So typically, these processes take from hours to days to in the atmosphere, and if the conditions in the chamber are similar to the atmosphere, it means the measurement in these chambers will take from hours to days, and it's not possible to measure transient emission sources with these kind of reactors because the residence time and response times are so slow. And one important thing is that different kind of wall losses of particles, wall losses of precursors can be significant in these kind of reactors, as the measurement takes so long time. The other instrument or reactor type are the oxidation flow reactors. So these are constant flow reactors with residence time only few minutes. So you can take the sample directly from an emission source or wherever you want to sample from. They have volume, the actual reactor volume is only few liters typically. You have also controlled humidity, UV radiation and intensity, and ozone concentration in the reactor. But the concentration of the ozone and the UV exposure, the UV intensity are much higher compared to the atmosphere, compared to the smoke chambers. So the amount of these oxidative components, the amount of hydroxyl radicals is multiple times higher compared to the atmosphere or the smoke chambers. So the benefits of these type of reactors are that they can be taken directly to the emission source, for example, the stack of a power plant. They have fast response times. You can get equivalent photochemical aging of several days in just few minutes. So the sample takes 1-2 minutes to pass through the reactor from the emission source to the instrumentation, and inside the reactor, the equivalent aging time can be several days, which enables also transient measurement because the response time is quite fast. Downsides of these kind of reactors are that you can measure one aging time at one time. So one set of parameters, you have the humidity, you have the UV intensity, and the ozone concentration. That translates basically to a aging time. So if you want to change the aging time, you have to change the parameters of the reactor. But this is quite fast to change the parameters. So changing the parameters, you can scan over the different aging times. The other downside is that the conditions differ greatly from the atmosphere, and there's discussion that does it describe the phenomena in the atmosphere or not, as the chemistry might change due to the very fast processes and high concentration of oxidative species. On the right side, the picture above describes it's a picture from Tampere University secondary aerosol reactor, and where you can see the glass tube, which is the reactor. The sample flows through the glass tube, and then there is an UV lamps above and below it. So that's the actual reactor part. The graph below describes how the number of publications where smoke chambers, and also known as environmental chambers, or the OFRs, have evolved during the last decade. You have to be noted that the number of OFR publication, they are multiplied by 3, so there is quite a lot more still publications coming with the smoke chambers, but you can see that the number hasn't really increased during the last years. However, there's a significant increase in the number of publications where OFRs have been used. I think no questions in the chat box so far. If you have questions, please write them to the chat box. Now we will focus on the OFRs more deeply. So here we have an oxidation flow reactor. We have the UVC lamps, and we provide water molecules and ozone to the reactor, and inside the ozone reacts with the water molecules when high energy photons are present, producing hydroxyl radicals. Some of the oxidation flow reactors use UV lamps with 180 nanometer wavelength, and these will produce also ozone inside the reactor. We are using only 254 nanometer lamps, which wavelength lamps, which will produce hydroxyl radicals. So our reactor and the example reactor here needs the ozone injection. So if we introduce the aerosol from the vehicle, in this case, we typically want to do a dilution to the primary, to the exhaust aerosol to mimic the typical dilution of the exhaust aerosol to the atmosphere. So when the exhaust emission and the other components are introduced to the chamber, we have the primary particles present, the hydroxyl radicals, and, for example, volatile organic compounds. When the processes go on along the reactor, the hydroxyl radicals will react with the volatile organic compounds, producing low volatility organic compounds. These low volatility organic compounds may nucleate or condense on top of the existing primary particles. These processes will carry on through the reactor, and in the end we have the aged aerosol, and depending on the conditions, so the UV intensity, ozone concentration, humidity, we might have achieved the maximum, so the potential aerosol mass. And now the aged aerosol is ready for instruments. We have one question in the chat box. In general terms, you are speaking about emission sources. Does this mean that the DOFR is designed just for high concentration emissions, or it could be used for environmental PAM measurements? Yes, you can use it for both, of course. I'm just using the vehicle emission as an example. There are some key benefits in the DOFR that makes it quite good for the, for example, the engine emission, vehicle emission measurements. So that's one of the reasons why I use it as an example. But we go to the details of the instrument next. Okay, so the Dekati oxidation flow reactor, the DOFR, it's based on the Tampere University reactor, so the chart that we saw a picture a few slides ago. Details about the reactor: there is 12 UVC lamps with wavelength of 254 nanometers, so these will produce the hydroxyl radicals when there is ozone and water molecules present. And any number of lamps can be switched on or off, and this is the way you can modify the UV intensity inside the reactor. There's a UV sensor that can be used to monitor the condition in the reactor to verify that all the lamps are working as they should, and so on. There's an integrated ejector diluter, which is a first stage of the E diluter, which is our dilution dilution system that Dekati provides. So part of it is inside this reactor system, and it is used to create the stable flow through the reactor chamber and provide enough sample for a large number of instruments. This is an important factor because of course the residence time inside the reactor chamber itself is a key parameter defining the aging time, how far the processes reactions will go. So with the ejector diluter, we can easily tune the flow through the reactor and maintain it steady. One key information missing from here is that the typical flow rate for this reactor is 5 liters per minute, and the residence time with that 5 liters is less than 1 minute. It's in the range of 40 seconds. It's designed inside of this quite portable case, so it's robust and portable, and there has been there has been a focus on the cleaning and maintenance part, so you can quite easily take the reactor apart and do the necessary cleanings before the measurements. And this reactor part is already available. So if you want more information, contact us or your local distributor about the actual pricing or etc. How does it look inside more closely? If we follow first the green arrows, which indicate the flow path for the aerosol, we have the inlet, and the aerosol goes through this so-called laminarization cone. Then we have the reactor chamber, UVC chamber, and after the chamber we have the ejector diluter here providing the flow and good amount of sample for large number of instruments. There is also 2 additional measurement points between the reactor and ejector diluter in case if you don't want to use the ejector diluter to minimize the dilution, for example, after the reactor, or for gas measurements before the ejector diluter. Here is a picture from the inside of the UVC chamber. So we have the glass reactor tube where the aerosol flows, and here we have the 12 UVC lamps. There's also integrated cooling for the UVC chamber. So we have a fan that is guiding air through the UVC chamber around the UVC lamps. Here are some results from the lab tests that we have made for the reactor. This is the laminarity test for the reactor measured with natrium chloride, so table salt, sodium chloride particles, so table salt. We have the dashed line, that is the input burst introduced to the inlet of the reactor measured with 1 CPC, and the other blue line is the output distribution measured with another CPC after the reactor. So this describes the how the input burst will transform inside the reactor. In an ideal case, the red line describes the ideal case. So it's an modeled with a fully laminar model, and you can see that the measured and the modeled are giving very similar results. So we can say that the flow through the reactor is laminar. Here are some tests about the maximum equivalent aging time. So we have, this is done with carbon monoxide. So it's a good indicator. The carbon monoxide is a good indicator for the aging time. So the carbon monoxide will oxidize inside the reactor to carbon dioxide, and measuring the change in the concentration of carbon monoxide, we can calculate the equivalent aging time. In the graph on the left side, we have only 2 UVC lamps active. There's 3 different humidity levels tested, and as function of the ozone concentration. So with 2 lamps active, we can reach equivalent aging times from 1 to 2 days up to 1 week. If we use all 12 lamps, we can, and high ozone concentration and high humidity, we can achieve even 1 month of aging, equivalent aging time. So the key benefits of our product of the Dekati oxidation flow reactor are that the flow through the reactor is laminar and the residence time is very short, which enables transient measurements. Here on the right, this is for the Tampere University reactor from their publication for that reactor, but this describes quite well also our reactor, as the key dimensions are same. There are 3 toluene injections, short bursts to the inlet of the system, and the blue line describes the produced secondary aerosol mass from these 3 peaks of toluene. In comparison, there is two lines with a different reactor type, which is not laminar, and you can see that you can't distinguish these 3 peaks from each other. You get only one large lump. So this describes the importance of laminarity and the short residence time if we want to measure these transient phenomena. We also, as we saw, we can get quite high a large range of aging, different aging times from just few days up to 1 month. There's an integrated flow control, so the ejector diluter, which ensures the stable flow through the reactor, and enough sample for the instruments. It designed to be very robust and easily portable to different locations. So how would you use the reactor in actual measurements? Here's an example setup for example, for engine or stack emissions. In the picture, we have a tailpipe here. Then we have a dilution system, for example, the E-diluter or E-diluter Pro. After the dilution system, we have to have some kind of sample conditioning, introducing the ozone and controlling and monitoring the humidity. And after that, the sample can go through the reactor, and then we can monitor the produced secondary aerosol with, for example, LP+. LP+ is quite good instrument for this, especially for the potential aerosol mass or the different mass evaluation. Here is a real example where we measured this Volkswagen Golf 1.4 liter gasoline vehicle, passenger car, and we tried to find the potential aerosol mass, so the maximum aerosol mass produced by this vehicle. We had the MPEG Plus instrument, which is also a new product of ours, monitoring the primary emission, and then we had an Dekati oxidation flow reactor combined with the HRLP Plus, measuring the secondary aerosol. And here are the results. The primary results are missing here, but they were really low. The primary emissions particle numbers were only few tens of thousands particles in cubic centimeter, roughly 20,000 particles. So there was not really contribution to the mass distribution after the reactor. Here we see the mass size distribution after the reactor measured with the HRLP Plus. We have a background first, which you can barely see on the bottom. So this is the secondary aerosol mass produced from the pressurized airs and so on, the sampling lines. They have always some potential to contribute to the measurement, but in this case we can see that there's no contribution, significant contribution. Then the different line colors describe different aging times. So in the first one we have only 2 UVC lamps active and reduced humidity. In this case, the humidity was roughly 25% in this case, and on the other it was 50. And here we increase the number of active UVC lamps in the reactor. We see that when we increase the number of UVC lamps, so we increase the aging time, the mass concentration goes up. But we noticed that with 8 lamps, we actually find the maximum. So when we change from 8 to 12, we actually see a decrease in the peak of the distribution. If we look at only the mass concentration value, not the distribution, we observe the same phenomena. So we get the maximum with 8 lamps active. These values are dilution corrected to the tailpipe conditions. Then few examples that I found from different publications where OFRs are used. In this there was an interesting combination of vehicle emissions and cooking emissions, but quite similar setup for use in both cases. So we had dilution, and there is the reactor and ozone generation, and then number of different instruments, aerosol instruments, site distribution measurements, and aerosol mass spectrometers. And here we can see the x-axis is the photochemical age of days, and the y-axis is the relative amount of secondary organic aerosol mass compared to the primary organic aerosol mass. The blue ones are for the vehicles, so we can see that the amount of secondary organic aerosol compared to the primary organic aerosol are about 100 times greater, so two orders of magnitudes greater, even more, compared to the primary emission for the vehicle. And for the cooking, it's the difference is not that significant, but there is 1 to 3 times more secondary organic aerosol compared to the primary organic aerosol. Then this is from the Tampere University of Technology using the char reactor. These are vehicle NDEC test cycles measured with the OFR. In the topmost graph, we have primary mass concentration with blue line, and the dashed line is the vehicle speed. We see some nice correlation here. If we look at the secondary mass compared to the primary mass, similarly as in the previous slide, we see that the values are roughly again 100 times more. So we have 100 times more secondary mass compared to the primary mass. And if we only look at the mass concentration of the secondary aerosol and compare it to the engine cycle, we see nice correlation between the mass concentration peaks and the vehicle speed here, so which describes the good time response of the char reactor. There was also one study of biomass burning. They had, again, there's the biomass burner and the stack, and then the sample is taken. There's a humidifier and the OFR reactor, and then the instrumentation. The dashed lines are for the fresh aerosol, so with the bypass around the oxidation flow reactor, and the solid lines are different aging times through the reactor. So we see a significant shift from to the larger sizes. This is number size distribution, so the median number size increases significantly, which means the mass has increased significantly. And the last thing I want to introduce the sample conditioning unit that is under development at the moment and will be available in 2023, so next year. The idea is to bring to the market a similar case that as the reactor part is, that can be easily connected with the reactor, and it includes ozone generation, humidifier, measurement for these important parameters, and we want to introduce a PC software that you can use to monitor these parameters and control these parameters. Yes, that was everything that I had about our new product and this new topic for you. Thank you. If you still have some questions, please write them in the chat box, or you can contact us afterwards. For example, the Dekati support. There's a question in the chat box. How do you take the UV sensor data? So I suppose you mean, yeah, how you can log or monitor it. At this point, when the sample conditioning unit is not yet available, we have for the I think you can see it in this picture, there's a table, there's a gray box next to the reactor. At this point, and if you only have purchased the reactor part, you get this separate control unit where you can control the ejector diluter pressure, so the flow through the reactor and the dilution, and you can select the number of active UVC lamps, and there are also connectors where you can use a multimeter to measure the voltage from the UVC sensor. But with the sample conditioning unit and the PC software, the value from the UVC sensor will be available on the software. Yes. I added one slide to the end of the presentation where you can find few publications made about the Tampere University DOFR, the char reactor, and some cases where it has been used. You can find, then this basically all this information, find this publication is also relevant for our product. So I will thank you. Okay. One more question appeared. Is there a way to know which lamps are turned off when running at 2, 4, 6 lamps and so on? I'm wondering about the UVC lamp position, which seems to be vertical. Yes, you can. Yeah, there are 12 lamps that are vertically or in 90-degree angle compared to the reactor glass tube. And yes, you can in the control unit at this point, you can select, you can turn on or off whichever pair of lamps you want. They are working in a way that one pair of lamps are controlled separately, and other 10 lamps are working as pairs. So you can choose whichever pair you want to activate or deactivate. This is still under development, how it will work with the PC software. Probably there will be option to do both. So there is just an this kind of slide bar or something that you can choose, turn on 4 lamps, and there's a predefined order where the lamps are activated, or you can choose certain lamps by whichever you want as with the control box. What about the irradiance homogeneity along the tube? Of course, the irradiance won't be completely homogeneous if you are turning only few lamps from the one end of the reactor. I don't know, does it, for my understanding, it doesn't cause really problems. And I lost my thought. And to minimize the effect, the box works kind of like a mirror, so it balances the effect. Next question, I want to know, how do you prove laminar flow? So basically, it is this measurement in this graph shows that the flow through the reactor is laminar. So the red line is based on a laminar model. So if we take this input distribution, or input burst, and use a laminar flow model, the outcome for the model is the solid red line, and the blue line is an actual measured line, the residence time distribution, and the difference between the modeled and the output is very small, indicating that the flow through the reactor is laminar. If the situation would be non-laminar, there would be some kind of more wide distribution coming out, some random peaks, for example, but now the shape is very smooth. In a perfect plug flow model, the input and output peaks would be identical, but kind of the laminar is the next best case that you can have in this kind of reactors. It's very difficult to achieve plug flow. Okay, more questions? Okay, maybe not. If you come up with questions, you can contact Dekati directly or your local distributor. I thank you once more, and I want to inform you that and advise you to register to the new Dekati portal. If you already have Dekati products, you can find important information about your product from there. And for all the HRLP Plus users, you can download the new Dekati data analysis tool free of charge from the Dekati portal. So for the high resolution LV Plus users. And as said, this webinar will be in the YouTube channel, and there is also a lot more good videos about our products. So check out. Thank you, and maybe we see in the future webinars also. Bye.